So we now know how to calculate lattice energy, but what causes some lattice energies to be bigger and some to be smaller? And to understand this, we're going to look at Coulombs Law. And the electrostatic force is proportional to the charge of the ions, but it's also inversely proportional to the square of the distance. So note that this applies to atoms of opposite charge. So let's say our cation and our anion. And energy is going to be equal to our force times the distance. Therefore, our electrostatic energy is going to be proportional to the charge of A times the charge of B over the distance. And that distance, how far apart they are, is going to be related to the radius of the cation and the anion. So if we look at this, the charge of the cation and the anion over the size of the radius of the cation and the anion are going to be proportional to the lattice energy. So just looking at this equation, what this is telling us is that bigger ions mean smaller lattice energies, because that size is in the denominator. So if we increase the denominator, the lattice energy is going to get smaller. But if we have a larger charge, and the charge here is in the numerator, that's going to give us a larger lattice energy. So the higher the charge of the ion, the greater the lattice energy. So here we've just got a visual for looking at this. Notice here we have lithium fluoride. We have the smallest of the cations, so we're rubidium, potassium, sodium, and potassium. These are all our alkali metals. And remember, they increase in size as you go down, so lithium is the smallest. And when we combine lithium with fluoride, which is the smallest of the halogens, we have the most negative lattice energy. So this is going to be the most stable. And if we use larger cations, so let's say rubidium and iodide, both of those are very large, those are going to have smaller lattice energies. So remember, the bigger the charge, the smaller the lattice energy. The bigger the size, the smaller the lattice energy. And the smaller the size, the larger the lattice energy. So just think about this if we were to do this as an iClicker question. Which of the following compounds will have the highest magnitude of lattice energy? So you'll have to consider size, and you'll also have to consider charge. And notice with each one of these, they all have the same charge. All the metals have +1 and all the anions have a -1. They all have the same anion, so that's going to be the same in each one. So that what's going to be different about each one of these is the size of the cation. So if we want the largest lattice energy, we need the smallest anion. So thinking back to our slide from the previous one, lithium bromide would give us the largest lattice energy, because this is our lithium bromide, this is our sodium bromide, this is our potassium bromide, and this bottom one here is our rubidium bromide. Okay, now I want to start thinking about why these ionic compounds crack. So we said that ionic compounds were brittle. Now remember, when we start off here, we have this lattice of the ions. So we have the cations and the anions, and everything's all nice and neat and orderly. And it forms this nice and neat orderly array because it's going to minimize the repulsions. So it minimizes the repulsions, but it's also going to maximize the attraction. So it's doing everything it can to get things of like charge as far away from each other as possible, but get things of the opposite charge as close as possible. And this is going to give us the most stable configuration. Now, if we hit this with a hammer and we start moving these planes of the cations and the anions, so let's see that we just hit it here, we've shifted things over a little bit. Notice that this external force destroys the orderly nature. And here we have like charges that are very close together, and they're going to repel each other. And when they repel each other, then the crystal is going to crack. So notice that this is not good, because now we've taken things that are opposite charge and moved them further away, and we move things that are same charge closer together. So this explains why ionic materials are brittle. Now, something else about the ionic materials. Now, in the solid form, so notice that here I just have sodium chloride table salt in a beaker, and I've got these electrodes attached to the light bulb. And you have the cations and the anions in fixed positions. So they cannot move because they're in the solid form. Everything's nice and neat and orderly. So when that happens, electricity can't flow and the light bulb doesn't light up. Now, if we melt our sodium chloride, so that's going to take a lot of heat and energy to do that. So here we have the electrodes into our molten sodium chloride. And when you melt it, the ions can start moving around past each other. And so you're starting to break some of those ionic interactions. And when that happens, the cations and the anions can move and they can carry the electrical charge, and we get a flow of electrons. And so the light bulb lights up. Now, another way that we can get the light bulb to light up is if we take our sodium and our chloride and dissolve it in water. So remember, the chloride ions are going to be surrounded by the positive ends of our water molecules to solvate it, and then our cations are going to be surrounded by the negative ends of our water molecule to help solvate it. And this breaks up the ionic lattice. And when it does that, the ions are free to move about in solution, kind of like they were in the molten form. But this time they're surrounded by water, and the water is a solvent that helps carry it. And in this case, since the charges can move back and forth, we get a flow of electrons and completes the circuit, and the light bulb lights up as well. Now, I just want to show you some of the melting points and the boiling points of some ionic compounds. Because remember, we said that ionic compounds, they're brittle, so we just explained why they're brittle. So if we apply a force and we change and we create some disorder in the structure, that they'll crack. We also said that ionic compounds will conduct electricity when they dissolve in water or when they're melted. But we also said that the ionic compounds have very high melting points, and this also means they also have high boiling points. So just to give you an idea of some of the melting points, like cesium bromide has a melting point of 636, calcium chloride is 782, and magnesium oxide has a very high melting point of 2,852. So I want you to think about, why is the magnesium oxide, why is that boiling point so much higher than that of the cesium bromide? So hopefully you're thinking about the strength of the lattice energy. So think about the lattice energy. So we said that bigger ions and smaller charge produce the smallest lattice energy. So cesium, that's one of our bigger ions, and it has a +1 charge. Bromine is one of our larger halogens, and it has a minus charge. So this has the smallest lattice energy. But then as we go to potassium bromide, potassium also has a +1 charge, and bromine is also a minus, but the potassium is a little bit smaller, so the lattice energy is starting to get a little bit bigger because we have a smaller potassium ion. Now going to the magnesium oxide, the magnesium has a 2+ charge and the oxygen has a 2- charge. And also the magnesium is pretty small in itself, and the oxygen is also going to be smaller. So the higher charge and the smaller radius gives the magnesium oxide a much larger melting point because the lattice energy is much higher. So the larger the lattice energy, the higher the melting point. And the same thing for the boiling point. So the higher the lattice energy, the greater the boiling point. Now I would like for you to pause the video and make sure, if you haven't done it already, to watch the covalent bonding video. So as we start looking at this, here we have two atoms. Let's say we have hydrogen. So here we have hydrogen and another hydrogen, and they're very far apart. This is equivalent of two friends being on opposite sides of the United States. And when they're that far apart, it's hard for them to meet each other or interact, and you're not really going to know what the other one's doing. So right now, these two hydrogens at 250 picometers, they're too far apart. And since they're too far apart, neither one is going to be able to detect the other one's presence. But let's start pushing these hydrogen atoms closer together. So now we're going to push it to 150 picometers. The atoms can detect the other atom's presence. So the proton on this hydrogen starts to see the electron on this atom, and vice versa. So they start to attract each other. And as you start pushing these electrons together, there gets to be this point where they get to be just right. And for hydrogen, that magic number is 74 picometers. So it's just right. There's a balance between the attraction of the nucleus on this atom for the electrons here and vice versa, and we're minimizing the repulsions of the nuclei, so the positive and positive charge, we want to minimize that, and we're minimizing the electron repulsions. Now if you push the atoms even closer together, let's say 30 picometers, this is just too crowded. You get too much repulsions between the protons, and you get too much repulsions from the electrons, and so they're not going to interact well with each other. So if we were looking at it graphs, you'll see this in the video. You start off with things that are too far apart from each other, so that's kind of our zero in energy. But as we get things closer together, we reach this minimum, and this minimum occurs at 74 picometers, where everything's just right. But if we push them too close together, the energy starts going up because it doesn't like it. It's just not favorable, and it tries to go back to reach that perfect value of 74 picometers. And this perfect value is unique for hydrogen, so the two hydrogens coming together. So here's that picture of the video. So here on the y-axis we've got potential energy, and here on the x-axis we have the internuclear distance, so the distance between the two atoms in picometers. So we started off where the two hydrogens too far apart from each other, they can't tell each other one is there, so the potential energy between them is zero. But as they get closer together, they're like, ooh, we kind of like each other. Let's get together. And so they can move closer and closer to each other till they get to this point where they say, you know what, this is close enough. This is my comfort zone. But if you get too close and you push them together even too much, then you start repelling each other again. So there's this perfect bond distance between these two. And for hydrogen, we said it was 74. And that 74 picometers corresponds to a bond energy of 432. So when the hydrogens come together and make a bond, it releases 432 kilojoules of energy per mole. So 432 kilojoules of energy is released to make a hydrogen-hydrogen bond. And in that case, since energy is released, delta H is negative. And since it's released and the energy is negative, that is an exothermic reaction. Now to break a bond, if we want to undo this, we're going to have to put in 432 kilojoules of energy. So it requires 432 kilojoules of energy. So in that case, the delta H is positive, and the value is endothermic if we want to break that bond. So using the Lewis atom, or the Lewis structure of the atom for hydrogen, they have one electron in its valence shell, and we're combining two hydrogen atoms. We can write this as H with two dots in between to show that there's a bond in between because it's sharing these two electrons, or we can write that as a dash, and that single dash there represents a single bond, and that means two electrons. So each electron pair between two atoms makes one bond. Now if we have two pairs of electrons shared between two atoms, that's a double bond. So we said this was a single bond. And if there's two, there's a double bond. And if there are three pairs of electrons between two atoms, this is a triple bond. So notice that it takes, so energy is released to make a bond, and to break a bond, it's going to require energy. And the deeper the well, the stronger the bond. So if you're just filling this in, that we want to notice that it releases energy to make a bond. Now we mentioned on the previous slide there were things as single, double, and triple bonds. So I just want to draw your attention to the nitrogen-nitrogen single bond, the nitrogen-nitrogen double bond, and the nitrogen-nitrogen triple bond. So what we want to conclude from this, and you can find other examples on in here, but the more bonds that there are, so the higher the bond order, the stronger the bond. So the more bonds between an atom, the stronger that bond is going to be. So notice for the nitrogen-nitrogen, if I want to break that bond, I have to put in 945 kilojoules per mole. But if I want to break a double bond for nitrogen, it only requires 418. And if I just have a single bond between the two nitrogens, I only have to put in 160 kilojoules for every mole of nitrogen-nitrogen bonds. Now just to kind of look at bond lengths and covalent radius, this is a reminder from chapter 8 as how do we define the covalent radius of an atom. So here the distance between the two radii, since they're both the same thing, we take that 143 and divide it by 2. So here I want to just draw your attention, we're looking at HF and HCl and then the HBr. So here we have the bond lengths 92, 127, and 141. So the fluorine is going to be, the hydrogen-fluorine bond distance is the smallest, because also the bond distance for the fluorine was smaller than the chlorine covalent bond, which was also smaller than the bromine covalent bond. So if we were to put these in order of bond lengths, HF is smallest, then HCl, and then HBr. And then again, we want to look at single bond versus double bonds. So if we're looking at a carbon-carbon single bond versus carbon-carbon double bond. So notice here that, remember we said the double bond is stronger than the single bond. Well, if the bond is stronger, that's going to cause the bond to constrict and it's going to get shorter. So the stronger the bond, the shorter the bond length. And we can make this comparison also with carbon-nitrogen. See 147 versus 127. So going from a single bond to a double bond, we've increased the bond order. And so that means that the bond has gotten shorter. So the bond order increases because we've got a double bond versus a single bond. So the bond's going to get shorter. Now this just kind of re-emphasizes what we saw in the previous slide. And the bond order simply means the number of bonds. So here we're comparing carbon-oxygen single bonds, that's bond order of 1. Carbon-oxygen double bonds, bond order of 2. Triple bond is a bond order of 3. So notice that the bond length got shorter as the bond order increased. So we have that inverse relationship. But as the bond order increased, the bond strength also increased. So it takes more energy to break a triple bond than it does a double or a single bond. Okay, so that should be enough to cover us for our first part of Chapter 9.